Hello, students. So this is our last installment on Newton's laws, and we're going to be talking about circular motion and how Newton's laws applies to that. So let me start by telling you about when I was a kid. When I was in high school, I flew model airplanes. And this was before drones and before radio control stuff was really available. And so in those days, you would fly an airplane, you'd control it using a handle that you would hold in your hand, and then it had a couple of strings, a string on the top, a string on the bottom. At the other end of the string was the airplane. And the plane would be going pretty fast around you. And if I wanted to make the plane go up, I'd turn the handle this way. That would pull this string. That top string would pull up an elevator flap and make the airplane go up. And if I went this way, the airplane would go down. So you can see what I'm talking about. I brought up. Okay, well, I had to change things around a little bit. My original video was taken down by somebody who didn't like the fact that I used their video of their airplane flying around. So I can't help that. So what you're going to have to do to see what I'm talking about is go to YouTube and type in control line planes or control line plane racing, and you'll see a bunch of videos of this kind of fun sport, to be honest. It's really primitive, but it's exciting. And anyhow, go ahead and do that, and then you'll know what I'm talking about. So we want to talk about the forces that are happening here. And so let's set up the terminology here. We've got a top view looking down. The guy is in the middle. Here is the airplane, and the plane is flying in this direction here. And that's the velocity vector. And now the really important here is the radius of the circle, or that would be the length of the string, really. And so here is let me just say that when I draw the letter R, I draw it like that, which is maybe looks a little bit like a V. I'm sorry about that, but that's the way I draw the letter R. Anyhow, R is in meters, and the angle that the plane has flown, this angle here, right, that's increasing, right, as the plane goes around. That's going to be theta in degrees or radians. We already talked about the velocity. And now there is something new here. When the airplane is turning, it's constantly turning, its velocity vector is changing, right? So later when the airplane, let's say the airplane is right here, here's the plane, its velocity vector is then pointing like so. And that's different from the original velocity vector. So that's a change in velocity. A change in velocity is an acceleration. It's not a change in speed, right? The magnitude of the velocity hasn't changed, but the direction has. But anyhow, it's a change in velocity, and so it's an acceleration. And this type of acceleration is called centripetal. It's a centripetal acceleration. In order to make an object accelerate, you have to supply a force, right? After all, Newton's second law is F equals ma, right? So we need, in order to get a centripetal acceleration, we need a centripetal force. And so that's what's called. The centripetal force is in newtons. And okay, now one last thing before I leave this picture. This velocity vector is called the tangential velocity. And the reason that it's called the tangential velocity is that if I were to draw a line that just barely grazes, I'm trying to do that here, just barely touches the circle, that line is called a tangent line, it's tangential to the curve, tangential to the circle. And so that's why we call this a tangential velocity. Okay. So we have some key formulas here. The magnitude of the centripetal acceleration is given by v squared over r. The magnitude of the centripetal force is m times v squared over r. In other words, Newton's second law. Force is mass times acceleration. Okay. So let's have a little example, put some numbers into these formulas. So if the plane were flying at 10 meters per second, and let's say the control string's length were 20 meters, and let's say that the mass of the plane is 800 grams, at 0.8 kilograms. In that case, what's the tension in the strings? In other words, how much is the guy pulling? So the answer comes from thinking, asking the question, well, what's providing the centripetal force here? Well, it's the strings that are providing the centripetal force. So all we need to do is figure out the centripetal force. So we have our formula, which is mv squared over r. So mv squared over r, we plug in our numbers, 0.8 kilograms. The speed is 10 meters per second. The radius is 20 meters. Don't forget to square up here. And you do the math, and you get 4 kilogram meters per second squared. But as you all know, kilogram meters per second squared is the same thing as newtons. So the overall tension was 4 newtons. Now there's a little detail. There were, 2 strings, one at the top and one at the bottom, and each string gets half of the tension. So each string really had 2 newtons. It's a little detail. Okay. So all of this is not too complicated. There are some things that I want to mention to you. First of all, the word centripetal means pointing inward. I think it's a Greek word or possibly Latin. I think it's Greek. Okay. Now, here's a question. Now, let's hide the answer. What happens to the centripetal force when the velocity is doubled? So think about it for a second. Here's a hint right there. Well, when the velocity is doubled, the centripetal force has to be 4 times as great, quadrupled, right? 2 squared is 4. So in general, the centripetal force and centripetal acceleration scale as the velocity squared. So this actually has some consequences, right? Let's say you've got something spinning, and you're worried about it, breaking apart. This could happen to a wheel or a merry-go-round, amusement park rides. And, it would be fun if the amusement park ride were to go twice as fast. Yeah. Well, okay, great. But let's make sure that the centripetal force, which is going to be now 4 times greater, right? You got to build your amusement park ride to handle 4 times more force, right? Okay. Okay, I already mentioned this. V is called the tangential speed. Okay, now, this is extra stuff. It's not in the book, at least not at this point. It'll come later, but I thought it'd be nice to bring it in at this point. You're not going to be tested on it anytime, before it comes up later, but still, here it is. The angle. I mean, we're used to measuring angles in degrees, but there is this alternative method called measurement called radians. So if you happen to measure the angle in radians, then the distance that the plane travels is given by a very simple formula. So radians have this advantage. They make these simple formulas happen. So here's the plane going around in a circle, right? It's going around and around and around. And let's say we're just talking about the time it took to go from here to here. How far did it actually travel? And so that the formula is the distance, the arc distance that it traveled is the radius times the angle. So that's real simple. If you measure the rate of change of the angle, how quickly is this angle increasing? If you measure it in radians per second, then you have a simple formula for the velocity, the tangential velocity, right? So that tangential velocity, V, is given by the rate of change of the angle times R, or delta theta delta t times R. And this works if you're doing things using radians. And yeah, in calculus it would be written d theta dt times R. All right, so let's put in some numbers here. If the plane goes 30 degrees around the circle, how far did it go? Well, okay, it doesn't work with degrees. We need to convert. So you're going to do use the fact that pi radians is the same as 180 degrees. So, okay, so 30 degrees times pi over 180. Notice that the degrees cancel, and you get 0.523 radians. Okay, now we can use our formula. We've got 20 meters for the radius, 0.523 radians, and you get the answer, 10.5 meters. Now you're going to complain. What happened? What about these radians, right? Shouldn't it be radian meters? And yeah, there's something about angles. We're going to get into this later, but radians and degrees are, I call them phantom units. They vanish. Whereas meters, they're real units, and they don't vanish. Yeah, you don't like that. But anyhow, I can't elaborate more at this point. And okay, here's a velocity example. Let's say the plane did that motion in 1/10 of a second. What was its speed? So the velocity is delta theta over delta t times the radius. Plug in our numbers, 0.523 radians, which we figured out before, the 1/10 of a second for the time, the 20 meters for the radius, and you get our answer. It's actually 104.6. I rounded it to 105. All right, so these are all really basic things, and honestly, things get much more complicated, and I'm not going to be able to explain the stuff that you need to do. You need to read the book. You need to study the problems. But I'll give you one piece of advice for doing rotation problems. And it's here. For each problem, you need to ask the question, where is the centripetal force coming from? So there's one of the examples in the book. A car is going around a curve, and here's this radius. As an aside, when you have a curve like this and a car is going around it, this distance from here to here has a special name. It's called the radius of curvature. So if you see this term come up, you'll see it come up. Radius of curvature, that's what it means. It means the distance from the center of the curve out to where the vehicle is going. Okay. Anyhow, getting back to my advice. Where's the centripetal force coming from in this case? Well, the centripetal force comes from the friction. It's static friction between the car and the road, the tires and the road. And so these problems become a combination of friction problem and rotation problem. Now, there's another interesting example, another interesting case. It's possible to make the curve have a bank to it. In racetracks, they typically will bank the curves. And there is a particular angle where if you have a perfectly banked curve, this particular angle for a particular speed of the car, where you don't need friction. And so in that case, where is the centripetal force coming from if it's not the friction? Well, it comes from the normal force, which you can decompose into a vertical part and then here's the important thing, a horizontal part. And so that horizontal part, that is providing the centripetal force. And then okay, now it's going to involve trigonometry, right? Because there's going to be this angle and all of that. But it's important to think about this the right way. The centripetal force is coming from somewhere. It's got to come from, in this case, the horizontal component. Now, maybe the car is going a little bit too fast for this particular banking. And now, so it's no longer a perfectly banked turn. It's not perfectly banked. So now the centripetal force is coming from a combination of the x component plus friction. Now the friction is going to be down this way, and so but now you're going to need to break the friction into a component that's this way, and then that's the one that matters. And then of course there'll be one that's this way, but that one won't matter so much. Okay. One last example, roller coaster loops. Well, where is the centripetal force coming from in this case? You got to ask the question, if you're designing this thing. Well, if the loop is sort of like perfectly designed where you define perfect to be maximum scariness for the passengers without killing them, that's when they feel they're going to have the illusion of being weightless right at the top of the current. It's like, I'm like an astronaut. I'm floating in space. In that case, the centripetal force is coming from gravity, it's the weight of the cars, the weight of the people, and so on. Now, they don't do that, right? Because they're going to be worried that people will try to jump a little bit and then they'll fall out of the roller coaster and kill themselves. So you actually do want the people in there to kind of feel like they're kind of still glued down to the chair. So in that case, it's a combination of things. It's the normal force that's being, there's the track here. The track provides a normal force this way, plus gravity, which is also helping. And so it's a combination of the normal force and the gravity. That's what is providing the centripetal force when you analyze this thing. So, okay, this is stuff that you're going to have to study by reading the book, by looking at the examples and actually thinking about how to do stuff. Work hard, don't give up, come to office hours, ask questions. Okay, thank you. Bye-bye.